We're pretty used to having a function and wanting to know its derivative. But what about going the opposite way? What if you know the derivative function, but you want to find the original function? That leads to the idea of an antiderivative. An antiderivative is just the name given to the idea of undoing a derivative. So if you start with the function, f of x, then the derivative, or ddx, the derivative operator produces a new function, which we've called f prime. And if you take another derivative, you get the second derivative. But to go the other way, if you had a derivative and you wanted to know the original function, this is the antiderivative. So the antiderivative of f prime is f, and the antiderivative of f double prime is f prime. That sort of leads to the question of, is it true that there's some function whose antiderivative is would go here? So some function whose derivative would be the original function. And that's an interesting question. That's something that we're going to have to wrestle with. If there is a function that's an antiderivative of your original function f, then we call it the antiderivative of f. And the notation that we'll use for it is a capital F, so just the capital version of the function that you started with. So an antiderivative, capital F of x, is the antiderivative of a function, little f, is just some function whose derivative is little f. So if you had an antiderivative, capital F, and you took its derivative, you would get your original function, little f. So I guess the name that we would put right here is capital F of x. Of course, then you wonder, is there an antiderivative of the antiderivative, and so on. So let's look at a couple examples of antiderivatives. So just for an example, let's find an antiderivative of the function sine of x. So remember, we want to find a function capital F of x so that the derivative of capital F is little f. Of course, little f is the original function sine of x. So can you think of a function whose derivative is sine of x? Well, let's see. If you start with sine and just start taking derivatives, eventually you get back to sine. So the function right before you get back to sine of x would be an antiderivative. So that's going to be, well, it's cosine, but let's check that. If you take a derivative of cosine, you don't get sine, you actually get minus sine. So to have a correct antiderivative, we actually need a minus sign out front here. So you can see, at least so far, given what we know about antiderivatives now, the only way we have to calculate antiderivatives is basically to guess, just to use our experience in taking derivatives to just guess a function that seems like it should be an antiderivative of the original function. That seems unfortunate that you just have to guess, but in compensation for having to guess, we have a way to always check our guess. And you can check your guess for an antiderivative just by taking a derivative and seeing if you get back to the function that you started with. So we are going to have to guess, but we can always check our guesses. Something that you might have noticed is that there's another function that we could have chosen. There's another antiderivative. So negative cosine isn't the only antiderivative of sine. What about negative cosine of x plus, say, 2? Well, we can check if this is really an antiderivative or not just by taking a derivative. If we take negative cosine of x plus 2 and take its derivative, what do we get? We get negative sine of x. Sorry, positive sine of x. So negative cosine of x plus 2 is also an antiderivative for sine of x. Well, you can see that really we could have added any number. So negative cosine x plus any number, say capital C, would work, as long as this number that we stick on the end here is a constant. So when we calculate an antiderivative, usually we're after the most general antiderivative that we can get. And that's always going to have some constant like this out in front, just to remind us that there are lots of different antiderivatives. So let's look at another example. Let's find the most general antiderivative of the function e to the 2x. So since this function is called little g, our antiderivative we would call capital G of x. And just based on our experience with taking derivatives, you'd probably guess that, well, the derivative of an exponential base e is something pretty much the same as the exponential base e. There might be some chain rule stuff that happens, but so the antiderivative should probably also be pretty much the same thing. All right, so that's it seems like a decent guess. Let's check that guess. Remember, when you're guessing an antiderivative, you can always check your guess. So if we started with e to the 2x and we took a derivative, we would get e to the 2x, but the chain rule would spit out a factor of 2. So actually our first guess isn't quite right. But that's okay, we can go back and fix this guess. So we need to modify our original guess for an antiderivative so that once this, if we did take a derivative and this 2 showed up, it would somehow disappear. So we need to stick something in front of here so that if you multiplied it by 2, it would cancel. Well, that's going to be a half. Then if we went back and put our 1/2 into our check and put a 1/2 out here, then these would cancel and you get e to the 2x, just like we wanted. So this is a correct guess for an antiderivative, but remember, this isn't the most general antiderivative. You can add any constant and come up with another antiderivative. So the most general antiderivative for the function g is 1/2 e to the 2x plus any constant. Let's find the general antiderivative of this function, f of x equals 3 over x squared plus 1 over x. Well, you can imagine that since derivatives happen term by term in a sum, antiderivatives will also happen term by term in a sum. So for an antiderivative, we can guess this piece by piece. Just like it's usually easiest to take a derivative if you rewrite all your x's as powers of x, if possible. That's true for antiderivatives too. So let's rewrite this as 3 times x to the minus second plus x to the minus first. All right, so now let's guess an antiderivative. Well, you would probably guess if taking a derivative decreases the power on x by 1, then an antiderivative should increase the power on x by 1. And that seems like a decent guess, so let's see if it works. Since the derivative has a constant multiple rule, right, if you took a derivative, this 3 would just sort of appear in your answer. An antiderivative seems like it probably also would have a constant multiple rule. So let's use this as our first guess. But if you remember, when you take a derivative, the exponent on x would come down in front. but our original function doesn't have a minus sign in front. So we have to somehow change this, our first guess at an antiderivative, so that if this minus 1 from the exponent comes down while doing the power rule, there would be something waiting to cancel it. So we need a minus sign out front here. Now let's look at the second part of this sum. So it seems like, well, we can just go through the same exercise. Since a derivative decreases the power on x by 1, shouldn't an antiderivative increase the power on x by 1? But x to the 0 is really 1. And if you take a derivative of 1, you don't get x to the minus first, you get 0. So this guess can't be right. So for most powers of x, you can find an antiderivative just by increasing the power by 1. But x to the minus first is actually a little bit special. Remember, x to the minus first, that's 1 over x. So we're looking for a function whose derivative is 1 over x. But wait, that's natural log of x. That's nothing to do with the power of x. It's actually just natural log. Okay, so now that we have what seems like a decent guess for our antiderivative, let's check just to make sure. While we're at it, let's write our plus c, because we need our constant out on the end. So let's check that this antiderivative is correct. And let's write down f prime. Remember, we're hoping that f prime turns out to be the original function f of x. Okay, so let's calculate a derivative. So in the first term, this minus 3 is a constant multiple, so that stays the same, times the power rule brings down that minus 1, and also decreases the exponent on x by 1, so we have an x to the minus second, plus, now the derivative of natural log, but the derivative of natural log is 1 over x, plus the derivative of a constant, but remember, the derivative of a constant is 0. Okay, and then simplifying this, negative 3 times negative 1 is positive 3 times x to the minus second plus 1 over x plus 0, but we don't need to write the plus 0. And this checks out. This is the original function, 3 over x squared plus 1 over x. So since we took a derivative and we got back to the original function, that means that this is the correct general formula for capital F of x. The antiderivative of f is negative 3x to the minus first plus natural log of x plus c.